Hi there. All right, so today we're going to look at graphs of basic functions. So these are all the graphs that you would have seen previously. We're going to kind of dig into them and look at them probably a little bit more differently than you did in Algebra 2, but also looking for some efficiencies in how we graph these. Tomorrow, it gets more in depth. We start shifting these graphs around and stretching them and reflecting them and such. And so we have to know the parent function inside and out before we get into tomorrow. First of all, though, a little bit of an introduction to the idea of continuity. A graph is continuous. The word continuity comes from continuous. So it is continuous if the graph can be drawn without lifting a pencil. So there's no breaks in it. You don't have like any jumps or holes or asymptotes, anything. So if you look at this example A here, the interval of continuity, well, it is continuous forever. Like I am going to draw this entire graph and that arrow shows that it keeps going and I can draw the entire thing, never lift my pencil. So the interval of continuity is just negative infinity to infinity. But if you look at example B, on example B, there's like this hole in the graph for whatever reason. So that breaks up the continuity. So when it wants the interval of continuity, I'd have to say, well, it is continuous from negative infinity until I get to 3. You're writing your x values always. So I can sit here and draw this and never lift my pencil until I get to a 3. So then I do a parenthesis here. And then it's still continuous after 3. So I'd say it's continuous also from 3 to infinity. So those are the two intervals of continuity. So the idea of continuity is kind of just a new term, a new concept for you. But most of what today we're going to look at is looking at graphing what we call the parent functions. So these are like the most basic functions you can have. So for each type, I guess. So a constant function. So the most basic constant function we can come up with is a y equals 0, I guess. And really, I could pick any number I want there, but it's just y equals a number. And if you have that type of an equation, remember from the other day that a y equals number is a horizontal line. So this is just a horizontal line, a horizontal line at 0. If it was a y equals 5, then I'd have a horizontal line at 5. Most basic constant function I could come up with. All right, so the next one is the identity function. And so the identity function is considered a linear function. And the most basic identity function or linear function I can come up with is a y equals, and I'm sure you're thinking mx plus b. Yes, but I'm going to simplify it to just an x. That's the parent function for a linear. If you look at it, there is no plus b, so it'd be a plus 0 out at the end. There is no m, so it's assumed to be a 1 there. So I can still graph that. It's going to have a y-intercept at 0, and the slope of it is a 1. So up 1 over 1, up 1 over 1, and I can continue doing this. Now, the reason they call it the identity function is because your x and your y value are always identical. All right, let's talk about some that are a little trickier than those. An absolute value function. The most basic absolute value function I could draw or write is a y equals absolute value of x. There's no coefficient. I'm not adding or subtracting. It's just an absolute value of x. If that is the case, then you would have your vertex right here at 0, 0. And I guess I'm hoping you know that this is going to graph like a V shape. And it's going to have your standard. It's almost like the identity function where you'd go over 1, up 1, and it would have that constant rate. Now, Really, we're probably going to get tied to some tables in some of these as we start getting into the harder ones. And you need to recognize, I guess, the slope, and I use that term kind of loosely. The rate of change is really what I should say. But if you put in a 1 into this function, you do get a 1 back. If you put in a 2, you'd get a 2 back. 3, 3 back. Now, if you put in the negatives, though, if you put in a -1, the absolute value is what's making that be a positive 1. -2 would get you a positive 2. So you can see I have the linear portion on this side, but then as I put in negatives, it's going to make it turn into this V shape. So for tomorrow, you need to know that an absolute value is a V shape. You need to know that the slope of this is just a up 1 over 1, up 1 over 1, up 1 over 1. And you just keep going up at that constant rate. Next, let's look at the reciprocal function. All right, the basic reciprocal function would look like this. Y equals, and instead of having an x, I have the reciprocal of x. It looks like this. Now, this table that I'm going to draw is going to be really, really long. So I'm going to go way down here. All right, so here we go. I'm going to start and I'm going to put a negative number in. I'm going to start and kind of move left to right as I go. So I'm going to put in like a -5 for your x. Now, what is the y going to be if you put in a -5? So I'm just putting a -5 right here. So it would just be a 1 over -5, -1/5. And then I could plot that. I'm left 5 and down a 1/5, somewhere like right there. All right, let's keep going. Let's try putting in a -2. Then I'd have a -1/2. How about a -1? That's just going to be a 1 over -1. That's going to reduce to -1. Now, I'm going to start putting in some fractions even here. So what if I put in a -1/2? Remember that you're doing the reciprocal function, and so all you do is you do the reciprocal of this. So if I flip this, it's going to be a -2. So if I put in -1/2, I get a -2. It goes right here. Let's try one more. What about a -1/5? If I do the reciprocal of that, I get -5. All right, so do you start to see the symmetry and how this is playing out? Now, this is the important one here. What if I plug in a 0? Well, if I put a 0 in for x, I'm going to end up with a 0 in the denominator, and that can't be. That's actually undefined. Something funky is going on my graph right there because that is undefined. And now I'm going to pick up again and do the same thing with those same numbers, but now they're going to be positive. So I'm going to put in a positive 1/5. So that means I'm going to go over 1/5. The reciprocal of that is a 5. So that means up 5. It's going to be right here. If I put in a 1/2, I'm going to get a 2. Over a half, up 2. Put in a 1, I get 1. Put in a 2, reciprocal is 1/2. Last one, put in a 5, I get a 1/5. All right, so now, honestly, I am looking at this and thinking, all right, well, I have all these points that I have to connect, and I can see that it's going to look like this, and it's going to curve around and head down. But the question is, how is it that I'm going to take this and end up back up high? Well, I cannot connect these two because x can never equal 0, so x can't cross over that vertical axis. I'm actually going to have to put in a vertical asymptote right there. And actually, if you look closely at this, you can see, oh, there's probably a horizontal asymptote also. Yep, the reciprocal function has a vertical asymptote and a horizontal asymptote right at the axes, and then it just has these 2 curves going on. All right, so for tomorrow then, my expectation would be that you know that when you see this type of an equation here, where your x is in the denominator, that this is what the graph will look like, and that you're going to have two asymptotes, and then you have these two branches of it that are in opposite corners like they are. All right, here's our next one, a square root function. The most basic square root function I could write is just a y equals square root of x. Don't put any numbers in, just square root of x. If I do that and create a table, I'm going to be very particular about what I plug in for x because I want it to square root nicely. So I might start with a 0. Square root of 0 is just 0. That works out nice. I could even put in a 1 because the square root of 1 is 1. But I don't really want to put in a 2 because the square root of 2 is not going to come out nice. So I'm going to jump to 4. And the square root of 4 is 2. What do you think the next number should be? 9. Square root of 9 is a 3. All right, let's plot these points. 0, 0, 1, 1, 4, 2, and then 9 is a little bit off my graph and up 3, somewhere like right there. All right, so here's what we have for a square root graph. Now that's your parent graph. It's going to start here at the origin. It's only going to go off to the right here. Notice there is nothing over here on this side because x can't be negative. Otherwise, I've got imaginary values. So that's why there's nothing on this side. You might notice the shape of this is a sideways parabola. Now it's only the top half because if I put in the bottom half, I would no longer have a function because it wouldn't pass a vertical line test. This does not have a plus or minus in front of it. It's just the positive square root. So I just have the top half of that thing. All right, so for tomorrow, got to know it starts at the origin and you got to know the shape of it. And when I say the shape of it, I'm talking about knowing this table right here and being able to do that table in your head and recognize I'm doing a square root. If I plug in a 1, I get a 1. If I plug in a 4, I get a 2. Plug in a 9, I'm going to get a 3. Plug in a 16, I'm going to get a 4. So knowing that table is what you need to come in doing tomorrow. All right, next one you're probably relatively familiar with because we use it so often. It's a quadratic, y equals x squared. That is the basic parent function of a quadratic. Let's make a table. Now, you probably know it's going to be a parabola, but could you plot the points on your parabola exact? That's what we want to do. So I'm going to put in a 0. Actually, I'll put in a negative. Let's put in a -3. If you square -3, you get a 9. If you put in a -2, you'd get a 4. -1 is a 1. 0, 0. And now we're to positive, so you're back to +1. And then a 2 would be a 4, and a 3 would be a 9. All right, now I'm going bigger than what my graph will hold because the graphs on your homework will go that far. And I want you to put in numbers until you start falling off of the graph on these. All right, so now let's plot these. -3, 9 is off my graph. -2, 4. -1, 1. 0, 0. 1, 1. 2, 4. 3, 9. And here is our parabola. All right, so the expectation on this one, when you come in tomorrow, you need to know that if you are looking at an x squared, that it's going to graph as a parabola. You need to know that the parent graph would start at the origin, and it's just symmetrical. In all honesty, futuristically, I'm only going to graph the right half, and I'm just going to know the left half matches it. Now, I also need you to know this table. This is your rate of change. It's not linear. It's going to change as it goes. So I'm going to start off, I'm going to go over 1, up 1. But since I'm squaring here, I'm going to go 2, 4, 3, 9. I need you to know this table part down here. Right, so it was kind of handy that I did the square root and the squaring on the same slide here, because it's worth noting here that these tables that I'm going to expect you to know really are just swapped from one another. And square rooting are inverse operations. And so really, if you just like remember the quadratic and just remember the square root is the opposite of that. Instead of going over 2 up 4, you're going over 4 up 2. Also, it's worth noting that this is going back several days to when we talked about symmetry and even and odd functions. Because this is an x squared and squared is even, then this is an even function. Even functions have y-axis symmetry. So y-axis symmetry is going to help me graph this. I really don't need to graph 6, 7 points here. All I'm really going to do is find my vertex, and then I'm going to graph these 3 points. And then because I know that it's going to have y-axis symmetry, I would just put their matching points over here on the other side. I'm not going to create a full table to do that. I just know the shape of it. And all right, let's look at a couple more parent graphs. So this one is a y equals x cubed. Now, for your table, now I'm doing tables today. Tomorrow, we're going to start trying to not get too caught up in doing too many points because we're going to already know what the shape of it, right? We're going to already know, right? So if I put in on this one, I'm going to put in a -2. If you cube a -2, it's going to stay negative. It's going to be a -8. If you cube a -1, it'll stay negative and be -1. If I put in a 0, I'll just get a 0 back. Now I'm going to go to the positives, put in a 1. Now it's going to be a +1. A 2 would be a +8. So you can see the symmetry here. So left 2, down 8, way down here. Well, it's really just right there. Left 1, down 1. 0, 0. 1, 1. 2, 8. You might notice that this is, let's go back to some of that symmetry we talked about a few days ago, that this is a cubic. It has an odd power, so it's an odd function. And odd functions are symmetric around the origin. And remember when we were doing our doing it algebraically, if you change the x to a negative, the y also changes. So if you had a 1, 1, that's great. But if you change this to a -1, right here, 1, 1, but if you make this a -1, like we did here, it changes to a -1 on the y. Let's look at a cube root. The parent function looks like this. I'm going to make a table so I can have some idea of what this is going to look like. I'm going to hand pick some numbers that are going to work nice here. So I'm probably going to choose a -8. The cube root of a -8, you can cube root a negative because the cube root of -8 is -2. Then I'd probably put in a -1 is the next nice one. And I'm going to get a -1. 0, 0. And then if I put in a 1 and cube root it, it's a 1. And then I'm going to jump to an 8 and cube root it. So it's nice that I'm doing this right after the cubic because you can see these numbers are really just swapped from one another. So now what's that going to look like if I swap it on a graph? Well, -8, -2 goes right here. -1, 1, 0, 0, 1, 1, and then an 8, 2. So what it's going to look like is like a sideways cubic wave. All right, so then tomorrow when you come in, I'm going to want you to know that a cubic is this little wave thing and the cube root's a sideways wave. I need you to know these tables, this whole 1, 1, 2, 8, and if you just know the symmetry, and this is part of why we do symmetry, do I really need all of these points? Or could I just do the positive ones and know that it's going to have origin symmetry, so it's going to have points down here in the negative range also? Let's talk a little bit about piecewise functions. I don't know that there's a great parent graph for piecewise functions. Really, we're going to just talk about how do I graph these again? And a piecewise function is when you take pieces of multiple functions. In both of these examples, I just have two functions, but there might be 3 or 4 functions. So what this is telling me is this piecewise function says graph this function, this linear function, but only graph it when your x is less than or equal to 5. This one says, hey, graph this linear function, but only graph it when it is greater than 5. Notice there's not going to be any overlap here. That's what keeps it a function. Now, typically what I do on this, because I like to use slope-intercept form to graph it, and even though when I do that, it may not be part of this interval, I'll just erase what I don't want. So start off, I'm going to graph this line. So the y-intercept is -3, and then I'm going to count rise 2, run 1, rise 2, run 1. And I'm going to do that a little bit. Don't get too anxious to quit putting dots. I'm really only concerned with this when x is less than 5. So I could keep going until I hit 5 and then just stop, which is where I'm at. So I want this graph, this linear graph, when x is less than 5. So it's going to look something like that. It does say or equal to, so I know that here at this 5 spot, that it does actually hit that. The next part is an x plus 4. The x plus 4, if I were to graph it, starts off here at 4 and then has a slope of 1. So rise 1, run 1, and you sit here and do that. I'm going to do it clear to the end till I get to here, and then assume it would just keep going after that. Kind of need a few more spots there. So I really only want this graph when x is greater than 5. So that starts right here, actually, except that I don't want it to equal 5 because it equals 5 down on the below there. So here's what I'm going to do. I am going to erase everything on this side because I don't really need that. Oops, my eraser got kind of big. Sorry. Let me redo that. And I'm even going to erase the 5. And what I'm going to do is I'm going to put an open circle at 5. Closed circle because of the or equal to, open circle because it's not. And then this is just a linear graph that has just kind of a different slope. It kind of flattens out. And it would look like this. That's 2 pieces of a function. But they don't really overlap because of the open circle. All right, so this next one, I'm going to go ahead and do this with you. The first equation is a 4 for a y-intercept, and then a -1. So down 1, right 1, down 1, right 1. And I'm going to keep doing this. I'm interested in this when x is less than -1. So I'm definitely having x values less than -1. I might actually go up here to this one. Because it's an or equal to, I'm going to want the one where x is -1. And I actually want it to be less than -1, so I really need to be going that direction instead. If you look ahead, you might have known instead of going down 1, right 1, you could have gone up 1, left 1, and gone the direction you wanted it to go. And I want everything this direction, like that, which means all those other dots I plotted, I really don't want those dots, so I'm going to get rid of them. Sorry, it was giving me a glitch there. So I don't want any of those. I'm just going to want the ones that went this way. Okay, so let's look at the next one. It's a horizontal line. That's what y equals 4 means, horizontal line at 4. And I'm interested in this when x is greater than -1. So it starts right here, but it's not an or equal to, so I have to put an open circle at -1. And then I'm just going to have a horizontal line going through here at 4. And that's the two pieces of my function. All right, probably the most common piecewise function is the greatest integer function. It forces you to always end up getting a y value that is an integer, regardless of what you plug in for x. And so when you're looking for the greatest integer function, you're always saying in your head, I need the biggest, largest, whatever you want to say, the greatest. I want the biggest integer that's less than or equal to the x that they give you. Now, if you think of a number line, and I'm not going to put a bunch of numbers on this because it'll never end up right, but I'll never have it big enough. I'm just going to put 10 and -10 on it. Okay, so what I'm wanting is an integer. I want it to be the biggest one I can without getting bigger than the number they gave me. So right here is a -4.2. So that's going to fall somewhere between a -4 and a -5. And right here is my -4.2. Now, I want it to be an integer, but I don't want it to be bigger than -4.2. And so bigger numbers are always to the right. They're always to the right. So that means I'm going to go to the left to make sure that it doesn't get bigger than 4.2. Because if I go over here to this -4, that's bigger than -4.2. Feels weird because you're in the negative range, but really, the biggest integer I could pick that's not bigger than -4.2 would be this -5. I don't want to pick -10. That's too far away. I want to pick the closest one, but it's got to be less than or equal to the number they give me. So that means it's got to be a -5 in this example. Okay, let's look at this greatest integer function for a 6.3. Okay, so a 6.3 is out here somewhere between a 6 and a 7. So here's my 6.3. I want the biggest integer, the closest one there, that's less than or equal to x. So I can't go to the right because those are bigger. I want it to be less than. I'm always going to go left. So right here, 6 is the greatest integer that's less than or equal to x. So I'd go 6. You're always going to go left. Always go left. Unless you end up with an integer itself. Because it does say or equal to. If I give you an integer, then it's just, that is going to be the greatest integer that's still less than or equal to the x. So same thing here. If I give you an integer, you just get that. All right, so let's get fancy here. Now I'm going to get this -1/2. All right, so a -1/2 is going to fall somewhere between a 0 and a -1. It's going to fall right here. The greatest integer, always go left, would be a -1. But then there's a negative in front of that. So that's going to change the sign on my -1, and I'm going to end up with a 1. All right, let's graph this to see what this would look like. I'm going to make a table real quick. And it could get really long, but I'm going to hope that we just get the pattern figured out and then we'll run with it. So I'm going to start off and I'm going to put in a 0. If I give you as an integer, then it is the integer. Now I'm going to increment by tiny amounts. So I'm going to put in like a 0.2. And then if you think on your number line, a 0.2 would be like right here, and you always got to go left, so it would be 0. If I put in a 0.3, it's still going to be a 0. Put in a 0.7, still going to be a 0. It's going to stay 0 until I hit the next integer. And when I hit the next integer, it's going to be that integer. And then if I put in a 1.2, that would land right here's a 1. So a 1.2 is right here. And I always go left. got to go left, so it's going to be a 1. And it's going to stay a 1 until I get to a 2. And then it's going to be, I'm going to squeeze that in, 2, and that's a 2. Okay, so here we go. Let's start plotting. 0, 0. And what this means is as I plug these points in, I'm going to stay at a 0. It's just going to stay a horizontal line is what I'm getting. I'm getting this little horizontal line until I get to 1. And when I hit 1, it pops up to here. And then it's going to stay a 1 until I get to a 2. And then it's going to pop up here. And this is your greatest integer function. It's sometimes called the step function because it just looks like a bunch of little steps. Now, I have one issue that I need to address. And this does even go, I could keep going with that same pattern left. Now, right now, what I have is not a function because I have a point here and I have a point here, and it wouldn't pass a vertical line test. So I have to put an open circle on one of the ends of this. And since I know I want 0, 0 to work right here, that means this end would be an open dot because I want 1, 1 to work right here. So what I'm going to do here is I'm going to go put close dot here, open dot here, close dot, open dot, close dot, open dot, close dot. And really, I don't even have to do the close dot. I'll just assume it's closed. So I need an open dot on the right of every one of these little guys. All right, there it is, the greatest integer function. Now those piecewise functions or greatest integer function type of equation, but this one here is a great example of where that might occur, and it's really not all that rare of a situation. So we have an express mail company, and they're going to charge $25 for a package weighing less than 2 pounds. Then for each additional pound or fraction of a pound, there's an additional charge of $3. So we're going to graph this function in the interval from 0 to 6. Okay, so what we want to do here is go ahead and make a table. And so if I were to pounds on the left, what it's going to cost on the right. So if I were to have a half-pound package, all right, it's going to cost me $25. If it was 1 pound, it's still going to cost me 25 pounds. If it was 1.7 pounds, it's going to cost me $25. If it's 1.9 pounds, it's going to cost me $25. But as soon as it hits 2 pounds, because notice it says less than 2 pounds. So I've hit 2 pounds. It didn't say less than or equal to. So once I hit 2 pounds, they're going to start charging me more. So at 2 pounds, it's going to cost me $28. And then it's going to stay $28 if it's 2.5 pounds. But as soon as it hits that next pound, then it's going to go up another $3. So now I'm at $31. And I could keep that going. 3.2 would still be $31, but when it hits the 4 pound mark, now it's $3 more. Now it's going to be $34. It's going to stay $34 until you hit the 5 pound mark. At the 5 pound mark, it's going to go up another $3. And then it says up to 6 and including 6. Well, my graph doesn't really quite go to 6. I guess it's only going to 5, so I might stop there. Okay, so let's come over here. What this means then, when I'm graphing this, when it is, the pounds are on the bottom. So if you think about this at, as soon as it starts, not at 0, because 0 I'm not mailing anything, but it's going to immediately cost me $25. So if you look at the scale, it looks like we're going by 3s. So right here is about at 25. Now notice I put a circle there because it's 0, doesn't really count, not going to cost anything. But it is going to stay this $25 the whole time until I get to 2 pounds. So at 2 pounds, though, it jumps up and it's 28. I'm going to do a closed dot at 28. And this is actually going to end up being an open dot because at 2 pounds, so this is right up to, I didn't make my circle quite big enough, but that's all right. So now it's going to hop up here and it's going to stay $28 until we get to 3 pounds. So I'm going to do an open circle at 3 pounds and it's going to pop up to 31. So that's right here. And now I'm going to keep it at 31 until I get to 4 pounds, open circle, jump up to 34, which is about right here. And it's going to stay 34. And then I'm going to go ahead and put an open circle at 35 because I know it's going to pop up here to 37 somewhere. All right, so that's what that graph would actually play out like. All right, that's all I've got for us today. Go jump into your homework. Good luck.